With a theory of logarithms, we can now solve exponential equations. For our first method, let's start with a checklist. So this will be when we can get an equation in the form base to the m equal to base to the n. First step, clean up as usual. Here our goal is to get our bases the same. If we can get b to the m equal to b to the n, we could just drop the b's to get the new equation m equals n. I solve for x, and then we check back in the original. Now, what's happening here? If I have b to the m equal to b to the n, okay, these are equal. If I do the same thing to both sides, we stay equal. So I'll apply log base b to both sides. The b's cancel, leaving me with m equal to n. And so that's going to be the heart of this argument. Now let's take a look. So I want to solve for x in the equation. 3 raised to the 2x minus 4 equal to 81. Here we see we don't have the same base, but I know 81 is a power of 3. That's just 3 of the 4. So our checklist says the 3's match, so I can just drop them and solve 2x minus 4 equal to 4. That'll get me 2x equal to 8 or an x equal to 4. We check our work. We go back to the original, so we'll have 3 to the 8 minus 4. That's going to be 3 of the 4. That's the 81 that we're looking for on the other side. So that checks out. Next, let's try 27 to the x equals 9. Here we need to get a common base. So 27 and 9 are both powers of 3. So we'll get, so 27 is 3 cubed, so we'll get 3 to the 3x equal to 3 squared. The 3's match, so I just throw them away. We get 3x equal to 2. I solve, I get x equal to 2/3. Now we check back in the original, so I have 27 to the 2/3. Okay, remember we could split this up. The exponent, I'll do the 1/3 first. 27 to the 1/3 gives us a 3. The cube root of 27 is 3. We square that, we get a 9, and then that's what we were looking for. So that checks out. Now, what happens when you can't get the bases to match? Then either your answer is going to be in logarithms, or you may be asked to put it in decimal form, so you'll need a calculator. For instance, if I have 2 to the x equal to 3, okay, first approach is just using the language for logarithms, so we have a dictionary. I could translate this to base is 2, answer is 3, exponent is x. In logarithm form, that is, okay, that's the exponent. X is equal to the log of the base 2 of 3. That's not on my calculator, but I have a formula that lets me get there. We could use either log of the base 10, log, or natural log, ln. I'll just use log, so I'll have log of 3 over log of 2. Calculator says when I round it to 3 decimal places, 1.585. Another approach, if I have two things equal to each other, we do the same operation. What comes out stays equal. So if I have 2x equal to 3, I'm going to apply log to both sides. What's going to happen, the 2 to the x, we have the power rule, which lets us bring the x out in front. Then I can divide both sides by log 2. Now, that'll give us our same answer, 1.585, so it goes to the same place. So that's another way to go. We check, of course, so if I take 2 to the 1.585, we'll get our 3 with 2 decimal places, so that sounds like we're in the ballpark. So that's a good answer. Next, let's try 4e to the 2x minus 8 equal to 8. Here, if I'm going to proceed, I need to isolate the exponential as usual. So what are we going to do? We're going to move the 8 to the other side. We have 4e to the 2x equal to 16. Divide both sides by 4. Now I have something in the form base to the exponent equal to an answer. I could either translate or I could just apply natural log to both sides. We'll do that one. So I have natural log of e to the 2x equals natural log of 4. Okay, 4 is just 2 squared. Natural log and e, remember natural log is log to the base e, so they cancel, leaving us with a 2x. For the natural log of 2 squared, I can bring the 2 out in front. We have 2 natural log of 2. The 2's go away, and we get for our answer x equal to natural log of 2. If we need to put that in a numerical form, we go to a calculator. Here, we're just going to take it as it is. We check. So where I have an x, we're going to put natural log of 2. What we'll do here, when I put it in, I'm going to leave the 2 on the outside the parentheses using the power rule. If I have e to the natural log of 2, e to the log of the base e, that cancels, leaving me with a 2. 2 squared is equal to 4, so I get 16 minus 8. That's going to give us the 8 that we're looking for. So that checks out. Now, in the other direction, we have logarithmic equations. So we'll proceed with a checklist as usual. First step is cleanup. What are we trying to get to? I want to have something in the form from our dictionary, log to the base b of a equal to e. So we're trying to get the logarithm isolated as usual. Once we have this, we have our language trick, which is just b to the e equal to a. You just translate. Solve for x, then you check. What's important about checking here, like with radical equations, you may get solutions, but those solutions fail when you put them back in the original equation. One thing to note about logarithm, for logarithms, they can only take positive numbers. Okay, if you put a 0 or a negative in, you'll get an undefined or it does not exist. So that's something we have to watch out for. Now, start off slow. If I have log the base 2 of x minus 4 equal to 4, we translate. So base is 2, answer is x minus 4, exponent is 4. We rewrite, so we'll have base to the exponents 2 to the 4, which is 16, equals the answer, which is x minus 4. We add 4 to both sides, and we get our answer, which is x equal to 20. We check. 20 goes back into the original, so we have log the base 2 of 16. 16 is 2 to the 4, and then the 2's cancel. The 4 comes out as promised. Next, let's try 2 times log of 4x equal to 4. First step is to isolate the logarithm, so we'll divide both sides by 2 to get log of 4x equal to 2. Then we translate. Now, no base means we're doing base 10. Answer is 4x. The exponent is 2. We rewrite and we get 10 squared is 100 equal to the answer, which is 4x. We divide by 4. I get a 25 for our answer. Of course, we check. So we'll have 2 log 4 times 25 is 100. 100 is 10 squared. So our bases match, and then we just get a 2 to come out. We multiply by 2. We get the 4 that we're looking for. Now, let's try one with a little bit more complicated rules and an answer that we have to throw away. So solve for x. We have natural log of x plus 1 minus natural log of x plus 4 plus natural log of x equal to 0. Here, I want to use the product rule and the quotient rule at the same time. So if we have a sum on the outside, we multiply on the inside. If we're subtracting a log, we're going to divide by that factor. So this all combines to give me natural log of x plus 1 times x over x plus 4 equal to 0. The log is isolated, so we could just use our dictionary to translate. So note, natural log, the base is e. Exponent is 0 here, so when we rewrite, I have x squared plus x over x plus 4 equals e to the 0, which is a 1. Now, that we could just solve as usual. I'm going to multiply both sides by x plus 4. The x's go away. We have x squared equal to 4. Using the square root property, we know we'll get x equal to plus minus 2. we have to check our answers before we can proceed. So if I take a look, if I take the minus 2, go back to the original equation, I'm going to take natural log of minus 2. That's a forbidden operation. We can only take the natural log of positive numbers, so we have to throw that away. For the 2, okay, we'll get natural log of 3 minus natural log of 6 plus natural log of 2. We put that together as before, so we'll have natural log of 3 times 2 over 6, or natural log of 1, natural log of 1 goes to 0. And so that checks our work. Let's finish with a compound interest problem. So we're going to start with $1,000. We'll have an annual interest rate of 8%. We divide by 100, that gives us R equal to 0.08. And our interest is going to be compounded monthly. So the N will be equal to 12. We want to know, how long does it take for us to get to $5,000? Now we're going to take our data and drop it into the formula, A equal to P times 1 plus R over N raised to the N times T. Our numbers go in, we get 5,000 equals 1,000, 1 plus 0.08 over 12, raised to the 12t. T is what I'm trying to solve for here. So we note the t is up in the exponent. I need to isolate the item that's raised to a power, okay, so the exponential part, so I'll divide both sides by 1,000. That gives us 5 equal to 1 plus 0.08 over 12, raised to the 12t. I could either go to a logarithm through the dictionary, or I could just apply natural log to both sides, worry about sorting out the numbers later. So let's do that. So I'll get natural log of 5 equals natural log, okay, we have our interest factor raised to the 12t. The 12t is on the inside, so I could use the power rule to pull the 12t out in front. I could solve for t by dividing by 12 and by natural log of the interest factor. So t is going to be equal to natural log of 5 over 12 times natural log of 1 plus 0.08 over 12. Be careful putting that in the calculator, and then what's going to come out for our time period, we're going to get 20.18 years. So 20 years to get to $5,000. Now, let's do the same problem, but let's change it up to continuous compounding. So this means we're going to have compounding every moment of the time period. Recall, the formula for this is going to be A equal to P e to the RT. So we put our numbers in, we'll have 5,000 equals 1,000 e to the 0.08t. Try to solve for the t in the exponent. To solve, I have to isolate the exponential part. So we have e to the 0.08t equal to 5. Again, I'll just apply natural log to both sides. Natural log of 5 equals natural log of e to the 0.08t. Okay, that's inside the parentheses, so that comes down. And I'll just divide by 0.08 on both sides. That's going to give me 20.11 years. So we note, if we use continuous compounding, we're going to get to the $5,000 slightly quicker than we would with the monthly compounding, but it's still going to be roughly 20 years.